Well, a very good morning to everyone here on the line. I hope you can see my screen right now. Thank you for your time, and I'm happy that many people will share our today's SOFinar. So my name is Martin Ziffling, and I'm together here with my colleague Akos Shapkash, who is here in the background. Well, today we want to deal with some questions according to creep and shrinkage. Before we start, I like to introduce a few little functions according to our online webinar system. So first of all, you will see a little hand symbol. So if you please can raise your hand so I get immediately the response if everyone can hear me. That's wonderful. Hands going up. Okay, thank you very much. The next thing is, in case you have any questions, you can post your questions in a so-called questions dialog below here, and we will try to answer your questions, if possible, right away. Usually we'll collect all your questions and we will send an email to all attendees later on with all questions and all the answers, so everybody will have a benefit of it. Okay, let's get started right away. So the scope of our today's SOFinar is creep and shrinkage analysis of beam elements. I want to focus on a recommended workflow for post-tensioned concrete beam bridges. And I also will introduce a few available methods to evaluate creep and shrinkage values. So we are gonna not to deal with shell elements and so on. This will be a topic of a upcoming SOFinar we plan to have next year. So today we will simply concentrate on beam element for post-tension concrete beam bridges. The recommended workflow I want to start first with, so everybody gets a little idea about how to set up a bridge project and how easy it is using the CSM tasks, the construction stage managing task inside the SSD to deal with all the creep and shrinkage effects. Nevertheless, it's interesting to know what's going on in the background. So what I want to introduce to you are a little bit more information about the background, as well as introducing a few little TEDdy numerical input examples where we can show you exactly what's going on, and so you will be able to reproduce it by yourself. As always, we will make a recording of this SOFinar, and we will post all the slides and as well as the little examples I'm talking about later on in our info portal on our website. So this is the agenda. Let's start with the recommended workflow, talk a bit about the CSM task, what's going on in the background, as well as I want to introduce a few options based on new features we just published in the brand new Service Pack 7 of version 2014. And again, if you have some questions, please use the questions dialog below. So the standard workflow of a bridge design followed by SSD and SOFI Plus is usually, I think everyone is well known by everyone. As I look on the attendee list, we have lots of experienced users here, so you know exactly how to set up an SSD project, define materials, define standard cross-sections, then you switch to SOFI Plus, where you define the bridge axis, bridge placements, where you define the master cross-section, again with variables following the bridge axis on all this. What you can do inside SOFI Plus. Everything is graphical orientated, so as well as defining some loads, you are fine and comfortable inside SOFI Plus. Now, after that, we start meshing our system, generate the real finite element system inside our database, and switch back to the SSD. Now, the next step inside SSD is to deal with construction stages. I think the construction stage manager is well known by everybody, so it's not necessary to introduce it to you, but nevertheless I will spend a few minutes on it explaining what you have to do, especially with creep and shrinkage questions inside the construction stage manager. So let's start right away with this little pre-stressed concrete bridge. I switch in my SSD project. First of all, so you see this little project, which is a standard SSD project, well known by everybody. I think you see here on the left hand side, we have our task tree, which is the, let's say, the contents of our project. Inside this you see some linear analysis, some traffic loads, as well as the construction stage manager. Playing a little bit around with the animator, I'm using the allow transparency mode. You will see inside the system, and if I zoom in, you will see that we're dealing with two cables or two tendons on both sides of our web, and we have a standard T-shaped beam cross-section here. That's all we want to go for. And the gray area you see here, we're talking about non-effective parts in the cross-section. So it's a very pure and very easy standard element. Switching back to my slides, I want to introduce now the CSM task, the construction stage manager, and I want to spend a few minutes explaining where you define something according to creep and shrinkage inside this construction stage manager. You all see now the a screenshot of this construction stage manager of the first tab. This is called stages, and we call it the first table, which is necessary to set up all the construction stages. That means in this table you define step by step what happens to your bridge project. You set up self-weight of the pier, you have some creep and shrinkage of the pier, you set up the self-weight of the bridge deck, you apply pre-stressing, again creep and shrinkage, you can apply additional loads, or you add additional supports, you remove supports, and so on. So everything what happens in the lifetime during the erection process of your bridge is defined here with a different stage number. The numbering is more or less free to you. What you see here, we follow a specific concept. That means in any case, we apply a new group of elements. We start counting with 10, 20, 30 with additional loads, and everything inside of 10 construction stages we are using for pre-stressing, creep and shrinkage effects, and so on. Marked with a red outline here, you see we have a few creep and shrinkage stages defined here. So the definition is quite easy. You simply say the stage number 15 is a creep and shrinkage construction stage. The type is C_1, so it's a creep and shrinkage action, category number 1. You see in the last line there's also a category number 2. This is necessary because we want to split the information up between all the creep and shrinkage effect until traffic opening and creep and shrinkage effects from traffic opening. The last 4 columns here in this table, you see we have a duration, a humidity, a temperature, and creep steps. So duration is very simple. That means you simply define how long this creep and shrinkage construction stage will last. So, for example, 28 days in the first creep and shrinkage step and 30,000 days in the last one. It's called 48. The humidity, which is important for the evaluation of the creep values, is set by 70% and the temperature to 20 degrees. The last column now is quite interesting because, as you can imagine, if you have a duration time of 30,000 days, it's not quite useful to evaluate the creep and shrinkage effects by just one single creep step. So you see here the input of the numbers 3. That means the program automatically divides the duration time of 30,000 days into 3 different creep steps. So it's just to gain some more accuracy inside the analysis process. And you're done. So that means in this simple table, you simply define creep and shrinkage steps, tell the program how long every step will last, and tell the program how many steps you will create. Beware of one thing. In the last line, we start with stage number 48, and we define 3 creep steps. That means internally the program creates a construction stage 48, 49, and 50. So based on the number 3, automatically 3 construction stages will be defined. So the next available free construction stage number will be 51. So you have to be careful about that. So this is the first thing we have to deal with. The second thing is in the next table inside our construction stage manager, you will see the table of group elements. As you know, all elements are organized in groups. These are beam elements, spring elements, constraints, shell elements, and so on. So you can switch on and switch off groups at specific construction stages. Also, you define a concrete age for the first loading, which is marked red again here. So this is also important. So for our group number 10 and 20, we define that the concrete is already 7 days old when we start loading it. As you know, by the development of creep factors, it's important to whether you start the concrete age with 7 days or 28 days or whatever. So this is something you define here, and you're done again. Now switch to the fourth step in our construction stage manager, the control panels. Again, marked with a red outline, you will see here 3 lines where you can have some features and functions to control creep and shrinkage calculations. So the first one is module for creep and shrinkage, AQB, only for beam elements. It's the default setting. So if you want to go for shell elements, it will be ASE named here. So we don't go more in detail right now. So let's leave it as it is. So for beam elements, AQB is the default setting. It's fine. The second line, creep and shrinkage for beam elements, is with the default setting of standard creeping. Leave it as it is right now. I will explain later on what other options you have. The third one, use creep and shrinkage according. There are different options, project design code. I will explain this later on as well. So don't mind if I simply skip this here. So we leave the standard settings as they are right now and go on. First of all, I switch back to my little example here. I open the CSM task. Now you will see it. And inside the CSM task, you will see basically exactly that. The same I defined before. And here we have different input settings. So usually as all times, the process immediately button is usually fixed. If you click OK and run, the whole construction stages will be analyzed immediately. At that point, I don't want to analyze it immediately because I want to show you where you can check the creep and shrinkage values on 2 positions. The first one simply in the report browser. So when we open the CSM report, you will see the creep values and the shrinkage values for every single group of elements. And what you see here in the first, in the top table, we have a group number 1, we have a beam element, we have an effective width of our pier and an effective width of our cross-section. And based on the different construction stages, you see here on top CS means construction stage. Below that you see the duration time of every single construction stage, 28, 28, 120. And here again you see in the last 3 stages, 48, 49, 50, you see the splitting of the 30,000 days in 821, 4,500, 24, 679 days. So this is based on the number of creep steps we defined before. Now these values are evaluated before, and this value will be simply used later on in the AQB file and will be processed. So that's what I posted here on the right hand side, PSC bridge, the underlined CSM dot you will see here, and you will see exactly what's going on with the creep and shrinkage values. I simply jump into this little example here. Now you will see it. So again, I scroll a little bit down. Here I'm in construction stage 25. I mark it now for you. And inside this construction stage, you see phi values, epsilon values. So what's evaluated in CSM simply will be added inside this AQB program module and will be processed. What is also very, very important dealing with creep and shrinkage and beam elements. I mark now the AQB module and the following ASE module. This is very important to understand. So simply imagine a square cross-section of 1 by 1 meter with 4 rebars in the edges. Now what's going to happen is, in case our concrete wants to shrink, the concrete starts shrinking, but the steel rebars inside the concrete worked against the shrinking process. That means that inside our construction we create stresses based on the shrinkage effect of the concrete, which is has a resistance by the rebar steel, and these stresses are caused only internally with no loads from outside. So we call them eigenstresses. And this is also shown here inside the input sentence, which is called Eige from eigenstresses, where we deal with that one. So this is the first effect of creep and shrinkage inside our structure, where we evaluate these so-called eigenstresses. Now we also have to deal with the second effect. Based on the deflection of shrinkage and so on, the whole structure wants somehow to deflect based on these effects. Now usually we have no single span beam, we have a continuous beam in bridge design. That means we have a static indeterminate construction. So based on this internal stresses and strains, the whole structure wants to deflect somehow, and based on the static indeterminate supports, the deflection is somehow constrained. So based on this additional constraint, we also get new forces and moments inside our system. And this will be evaluated in the following ASE program module. Here you see a new load case will be evaluated, which is based on the primary loads we had already defined, or based on the construction stages before, and what you see here, 60-25. So this is the load case containing the eigenstresses we defined before. So I mark this again. So we have the 60-25 here. So important for you to know, creep and shrinkage will be or we use creep and shrinkage always in a package of two load cases. The eigenstresses 60-25. So 6,000 is the basic load case number, 25 is the construction stage, contain the eigenstresses based on AQB, and the 50-25 and also 40-25 contains the additional constraint forces and moments based on these eigenstresses. So later on, if you watch the design process, this is nothing we will see right now. I think you have seen that in the load case table. You always have combination of two load cases. Simply open right now the CSM LF.dat. This is an additional data file created by the construction stage manager, which contains all the load cases with additional information about the construction stages. And what you see here, you see again that the first creep step 25 contains a pair of load cases, 50-25 and 60-25. Exactly the same goes on later on with 50-48 and 60-48. So just remember, in terms of pre-stressed concrete beam bridges, or for beam in any case, we always deal with two load cases later on for the design. Okay. Now the next thing I want to introduce now is I want to show you how you can check what's going on in the AQB. So again, I want to point your view to the underlined csm.dat file. And this file looks like that here. You have lots of template functions defined here. And there's also an echo option, echo force combination stress Eige. Usually you will find a no there. This prevents a long output, makes less paper, but this also prevents you of seeing what's going on in AQB. And for that reason, here we are. For that reason, I switch back into this PSC bridge underlined csm.dat file. And what I did here in this little information, this is a small trick I want to introduce to you. I simply make a $sign before the no. So I want to use the default setting for the output. And if you click on the report browser, you will see now the effects of creep and shrinkage, and you will get a more extensive output from the from that what's going on in the creep and shrinkage analysis in the background. So what we do have here for our group number 2, it's beam 20,000 or 200,001. So you see here we have the effective width again with 551 millimeters, and you see something which is new again. You see the phi basic creep, drying creep, the phi autogenous creep, and the drying shrinkage, epsilons for shrinkage, the autogenous shrinkage and the drying shrinkage. And what you see here, you see a full value. To explain this a little bit better, I prepared a little slide for you. Here we are. So inside the slide, you see again the table of CSM with the, in this case, creep values, and you see the output of AQB I showed you right away. Now, in this case, when the creep and shrinkage values are evaluated right away, you will find exactly the same creep and shrinkage values again in the output. So the basic creep is 0.62. You will find the 0.62 here again. And inside the final results for every single beam element, you will find a phi value, which is 0.59. which is marked red here. And this is simply based on the fact that there is a factor of different reference E modulus inside this whole calculation. That's what you see here. Phi equals 0.62 divided by 1.05 equals 0.59. So that's the value you see here. With the light blue frame, you will see here, I pointed it out here in the slide. You will see some general input which is of no influence. So AQB simply plots the default settings of relative humidity, temperature. You see here the value RH for relative humidity with 40. You remember we defined something with 70%. And there are some values of duration and age of concrete age and so on. This is simply plotted here and has no influence. Okay, leave it like it is. As now you may watch the slides later on if you download it as a PDF. Again, the same for shrinkage values. Here in this next slide, as I already explained, the construction stage 48 contains in total 3 creep and shrinkage steps, finally ending in construction stages 48, 49, and 50 with the different time zones, and the full shrinkage value is evaluated here again. So this is a standard setting and how CSM deals with all the effects. In the next slide, just a few information about the AQB manual. So what you see here is a screenshot of the brand new manual published with the SOFiSTiK 7 of version 2014. So the most important change is here that you see in the explanations of the internal stresses, that we changed the output from simply plotting the letters phi, phy, so we have now Greek letters for better understanding. Okay. Now I want to jump a little bit deeper in the background. So all I explained to you before was more or less the standard process: setting up your system, setting up your construction stages, defining creep and shrinkage with the standard settings, and simply analyzing it, and that's it. Now, to watch a little bit more in detail, I want to present this little slide. What you see here is the control beam and the control creep are two basic control parameters inside the CSM, where you can select different options. Now, as I explained before, control beam AQB is set, and this is something you need for pre-stressed or composite cross-sections. With the second option, control creep, you have two options. The control creep stan applies the standard creep and shrinkage procedure. That's what I already introduced right now. That means the creep and shrinkage values will be evaluated a priori by CSM, will be copied inside the AQB program modules and simply processed. The second option here is to use the control creep R creep. We call it real creep. That means that the shrinkage values still will be evaluated before and simply will be processed in AQB, but the creep factors will be now generated inside AQB. And this looks then like that. Now, this little slide for beams is the first introduction in a very little example Akush prepared for this SOFinar. And this will show you the differences. So what you see here is the difference between the standard creep and the real creep. We set up our system starting with the time t0, then nothing happens. At time step t1, we apply a load. The load is constant until a specific time t2, and then we unload our system. No. Now, in the next line here, in this slide, you see the development of the phi values of both structures. For the standard creep, the phi value starts at T0, and you see the standard development of the phi value following this green line. And this is more or less exactly this here on the left-hand side. Now we're applying a load from T1 to T2. So during the time when we apply this load, the phi value, which is this yellow area here, or represented by this yellow area, will be used just for this time period. And this results in the last diagram here. It's more or less the vertical displacement is plotted. So with our system with no loads, we have no displacement. Then we apply a load. That means we have an elastic deformation. Then the load is applied for a certain time period. So inside this time period, we have an additional displacement based on the creep effects. Then the curve goes up. Then at the time step T2, we unload our system. That means the linear elastic displacement will be taken away, and we remain with the final deformation. Now, exactly the same will be handled slightly different when we're using the real creep. So using real creep means that the creep value for every single time step will be created new, starting at 0. So what you see here is we start loading our system at T1. So in this now larger area, yellow area, represents the phi value. And then at time T2, we start unloading our system. And what happened now is, at T1, we have exactly the same linear elastic deformation you set. Then we have an increase of the deformation based by the creep effects. At T2, we unload our system. And then what happens now? It's what we call it's some sort of a relief. So if we unload the system, the concrete acts again in the opposite direction. So after the linear release of the displacements, we still have a decrease of displacement based on the relief effect of this creep of concrete. So this is how real creep works. Now, this is theory. How does it look like for a little example? Again, we created a very little example. It's a single supported beam. We apply a bending moment on both sides. That means we have a constant moment over the whole system. Both beam elements are, we have two beam elements, one in group 1 and one in group 2. And the difference is that at beam element group number 1 is more or less 20 days old when we apply the first load. The first load is 0, so nothing happens. And at time step T1, again after 28 days, we apply a second load. And the second load after 28 days will be removed again. So on the right hand side, you see the sketch group 1 with control creep stand, so that's what's going to happen. We have a very little creep effect here. In our group number 2, we simply start loading our beam at 56 days. So it's 28 plus 28. We apply the load for 28 days and then we remove it. So how does it look like? Here we are. So as already mentioned, you will find these examples later on. So it's a very simple one. So more or less just two beams, nothing very interesting. But the most interesting thing for you is that in this file here, so we simply control different effects. So the first control, which is important for you, is here. There's a control emod no. So this little control button here this option is for the stiffness development of the new concrete. So what we're doing here is we don't want to take into account any changes of the E modulus during the time period because we just want to compare the effects of standard and realistic creep. So this will be controlled by control creep stan or control creep real creep. And inside this data file, I simply run the CSM 2 times, and the only difference here is that the control creep arc is applied in the second one. The construction stages are quite easy. We have 4 construction stages where we apply a load, and what you see here with the loads, the first load we apply is very little load. It's more or less a 0 load, just to see the effects, what's going on here. So I already plotted the results, and now you see the differences. So with the standard creep effect, that means that the group number 1 is on the left-hand side here of the 2 beams. So that means we have 28 days with no load, and then from 28 days to 56 days we apply a load, and the creep value is derived by that one. Just one slide back, you see this yellow area, so we have a very little creep value here. So this results in a displacement of 0.35. On the other side, where our concrete is already 56 days old, when we apply the load, we have a totally different displacement. Yeah, so the differences of the creep values between start and end point of a load will be used for the standard creep. Doing exactly the same with the real creep, you see that the results are matching perfectly. The difference is on the right hand side, the displacement is evaluated by just 1 creep step, and for group number 1 the displacement is more or less evaluated by 2 creep steps in this case. The final results are exactly the same. Now, looking at the time, to speed it up a little bit, I want to very briefly introduce a next little example. In this example, I want to show you what's happening with the relief of the concrete, and this little example is done in exactly the same way. So we apply a load, and then the load is constant for a specific time, and then we unload our system. So what I did here in the next slide, now you should see the slide, I simply made a copy of the creep values from the report browser output, and in the first table, or in the top table, you see we simply be following the standard creep effect. So in this case, I applied very lots of creep stages just to split it up a little bit more in detail for a nice little plot here with an Excel sheet. And you see here, for this beam element, we have a final creep value of 1.37, and that's it. In the second table, or in the lower part of the table, you see we have exactly the same creep values, the development of the creep values, but we also have the output of the relief creep or the real creep effects. That means what happens after we unload our system. And here on the right hand side, you see exactly now the results I introduced before in this little slides with this little green and red lines, the displacement. So you see standard and real creep, the increase in the displacement after applying the loads are almost the same. Then we unload our system, and the blue line simply subtract the linear elastic displacement and then remains on the more or less displacement based on the creep. And the brown line will decrease in displacement based on the real creep calculation. So for the stress, for the forces development and so on, the results are identically. So if you're interested in displacements during the erection of your building, we recommend to go for the real creep evaluation. You see here in this little slide exactly what's going on. Okay, I want to stop now with the creep. I want to talk a little bit about shrinkage. What you see here in the next slide. It looks like very complex, but I try to explain it as easy as possible. Basically, what you have to know is that the shrinkage effects can be split up into two types of shrinkage, the so-called autogeneous shrinkage and the drying shrinkage. The difference is that the autogeneous shrinkage starts right away after you pour your concrete in the formwork. Then it starts right away. The drying shrinkage starts when based on your concrete handling. So if you take care of your concrete, if you leave it in the formwork, if you put some cover on your concrete to prevent the concrete of drying out very quickly, you can control a little bit the drying shrinkage effects. Finally, the total shrinkage is nothing else but the blue and the green curve added together. So that's what's going on here. Now again, there are two things which are very important for you in bridge design. You see a red area which is called TS smaller than T0, and you see a yellow area here where you see TS equals T0. So what happens now? The standard procedure is, and I have to go back a few slides, sorry. Here we are. Now you should see it. In the output of the CSM module, below the table of shrinkage value, you see a small sentence. In case of TS lower T0, shrinkage from TS minus T0 is not taken into account. Losses due to shrinkage are calculated starting at time T0. What does that mean? Switching back to my slide. So that means, talking about the red bracket here, that when we apply shrinkage, shrinkage will be taken into account from a time T0 up to a time value T, which is the duration time of our creep and shrinkage period. So we are using only this little amount of shrinkage strain or shrinkage deformation, whatever you want to call it here. The background of that is quite easy. So imagine if we are talking about a pre-stressed or post-tension concrete bridge. So that means all the shrinkage effects which are in the formwork, which are before you start pre-stressing your systems, are usually of no interest for the ULS design. Yeah. So you are interested in the losses of your tendon stresses based on the creep and shrinkage, or here of the shrinkage effects right after you start pre-stressing your tendons. And that's exactly what happens here. So for that reason, you have a relatively small amount of shrinkage value here. So this is more or less the concept we follow up in the CSM. So, and that's the reason why you have very low shrinkage values. This is based on experience of the last 25 years. It's quite okay. Now, in terms of composite sections, for example, or you're interested in the deformations during all these construction stages, you have to deal a little bit more in detail with that. Then you have to use an input where TS equals T0. That means you say T0 equals TS equals 3 days, whatever. That means the shrinkage will be value will be evaluated right from the TS equals T0, so the full drying shrinkage will be used here. The difference is that the autogeneous shrinkage effect from time 0 up to time where you start your shrinkage process is never ever used inside this shrinkage, inside this shrinkage values. Now, explaining about the differences here, again, we prepared a little example. This little example goes that way that we have exactly the same starting value, 28 days. Then shrinkage starts at 3 days in the first group, and in the second group shrinkage starts again at 28 days. And what you see here is, again, what I tried to explain before in this little output table here on the top right side of the shrinkage values. In the first line, the total shrinkage effect, if you do a hand calculation, is minus 180 times e over minus 5. No, minus 6, sorry, is larger than in the second group of elements, but nevertheless, based on the time duration we are looking at, the effect we are subtracting from it. So if I go back in this little diagram here, so the time from T to T0, we're only looking at that. So TS up to T0 will be not used in this case. So the 94 will be subtracted by the 180, and we end up with a shrinkage value of minus 86.3. In the second group of elements, the total shrinkage effect, if you do a hand calculation, is smaller than the first one. But based on the fact that TS equals T0, the effect we're taking into account is larger than in group number 1. It's a little bit complex to understand. I think you have to think about it later on. You will have the examples here. I just want to point out this effect. Important, I think, is to have it in 2 words, is for pre-stressed concrete beam bridges, use TS smaller than T0. For composite sections, use TS equals T0. This is what we define in CSM. Okay. Now, looking at the time, I want to introduce a new feature. We published now with the Service Pack 7 2 weeks ago, or 1 week ago, more or less. So that means, as I mentioned before, inside the CSM, you have an option, use creep and shrinkage according. Now you have basically 4 options: EN, European Norm 1992, or the FIP Model Code 2010, or the CEB FIP Model Code 1990, or there's a Rouge summation, which is an older one, according to the old DIN 4227. So at that stage now, you can select whatever you want in this option here. Talking about the numerical input, I know that a few of you like the TETI input more than the SSD input. Nevertheless, in CSM, it's called Control Option Eige Val MC10 for Model Code 2010. Or you can do exactly the same in program AQB. It's with the control option Control Eige Val EN10 is the European Code 1992, or MC90 is CEB FIP Model Code 1990. MC10 corresponds to FIP Model Code 2010, and some corresponds to the Rouge approach according to the old 4227 code. So this is something new, and if you apply that one, you will see it in this slide right now. I made 2 changes in our CSM task. So back again to the graphical dialog-based input. The creep and shrinkage for beam elements now I change the default and I want to have the advanced creeping. That means the R creep or real creep, as we talked about. And I explicitly select the year 1992 for the creep and shrinkage effects. And what happens now is you see the output changes that way that first of all you see in the output the analysis according to. And you see here, you see an additional line in the AQB output introduced with the beta T0 value of 0.3. And finally, you see the phi value used inside the calculations is again the 0.59 we had before. But how can you evaluate that? Very easy. You see the formulas here. It's just 1.87 times 0.33 divided by 1.05. Remember the factor of the different E modulus, and we said we get the value 0.59. Again, here in this output, the light blue frame is the default sorry, not the default settings, but now you see here the values from the CSM input from table stages will be plotted here. This is the difference according to the slide I showed you before. Now you see the real values which are used inside AQB to evaluate the creep values. Nevertheless, what you see here again, the shrinkage value will be used by the previous a priori definition inside CSM and simply will be used here. If you go for AQB standalone without CSM, you can use these input values, relative humidity and so on to evaluate the epsilon value as well. And this is a very good bridge to the final slide, tips and tricks, where you can find the information in the SOFiSTiK verification manual. I just jump one slide forward. So now you should see this slide. As you might know, we spent quite a lot of time to develop our SOFiSTiK verification manual, and I'm really happy that we do have that in 2014. And you can open this verification manual very easily from TEDdy menu help, as well as from SOFiSTiK structural desktop menu help. It's called SOFiSTiK verification manuals. We're talking about 390 pages right now. It contains 3 main chapters, and in the last chapter we have some design case evaluation examples, and there you will find 3 little examples, a creep and shrinkage example according to German annex of European Code 1992, exactly the same example to FIP Model Code 2010, and the same example to CEB FIP Model Code 1990. In the verification manual, you always see on the top a small overview, and if you click on the creep and shrinkage.dat, these files are linked directly, so you will find the files right away. So just going one slide back, I just want to point out a few tips and tricks which is very important for your understanding. The first thing is the question about the effective height of the beam cross sections. Now, in case of the standard creep and shrinkage procedure, what I introduced first, you have to take care about these different beam cross sections. What you see in this table on the right hand side is a little example. I just open it for you right now, so you see what's going on. So it's more or less exactly the same. So I have cantilever beams with different cross-section types. So the first row here is the same material, the same group and different beam elements. The second row, from here I just mark one element so you will see which row I mean. The second row is defined by exactly the same material but different groups of elements. So every cantilever beam is organized in different groups. And the third row now is organized with exactly the same group of elements but with different materials for every single cross-section. So finally, what you see in the results, and this is very important, we're talking about standard creep process. In the first row, you see the effective height. It's a value of 0.535. So it's nothing you will find in any of your cross-section. It's something like an average. And the total creep value is 0.63. The second 4 rows, you see we have material number 1, but we have group number 11 up to 14. So for every single cross-section, you will get an effective height value and the correct, and for this cross-section, the correct creep and shrinkage value. The last 4 rows, again, we have the same group, but we're talking about different material numbers, so you see exactly the same. So in terms of standard creep and shrinkage, again, please use in your structure different groups or different materials for different cross-sections to be sure that the different effects will be used properly. If you go for control real creep, the second line here, the effective height is calculated for every single cross-section in Aqua automatically and will be also used automatically. So you don't have to care about that later on. But there are two differences. So this is very important. And the last tip I want to give you is creep and shrinkage for composite sections. As I mentioned before, the input is T0 equals TS. For example, you start with 1 day because immediately after the concrete is poured on your steel structure, it starts shrinking and then you have stresses and forces inside your structure and you want to take care about that. So we have it almost 12 o'clock German time right now. I hope I could give you a quite a good overview about the creep and shrinkage effects inside our beam cross sections using the recommended workflow with the SSD together with the CSM task. I try to explain a little bit about the background of the standard creep and the real creep, as well as the shrinkage values we have here. And in the end, I see we have a few questions here. As I told you before, we will deal with the questions later on and send the answers to all of you. I like to thank you for your time and for your interest. So we have many people here attending today. We will publish our recording and the data, as always, in our info portal, www.SOFiSTiK.com/info portal. In case we do not get in touch in the next few days, I wish you all a Merry Christmas and a Happy New Year. And I hope we get in touch next year again. I wish you a good time and not too much work, and many luck to finish up all your projects so you can have a relaxed few days off between Christmas and New Year. Thank you very much, and see you again here on our SOFiSTiK SOFinar line next year. Bye bye.